Good morning, it's Jeremy. It's Wednesday, January the 14th. Today I want to talk about simulation using real and complex signals. About 15 years ago, I started using Psychos and Psychos Lab, and basically when you're using that software program, you're dealing with real signals. But if you get into using GNU Radio, you also have the ability to use complex signals. So just a quick review of the differences between the two. So here's some math here. If you do the Fourier transform of a time function s of t, basically you integrate from minus to infinity of s of t times the exponential of minus j omega t dt, and to get the inverse Fourier transform, you do the same thing except instead of s of t, you have s of f, and you multiply by plus j 2 omega t df. Omega is 2 pi times the frequency, where omega is the angular frequency. Now, there's this thing called the Dirac Delta function or impulse function. Basically, it's a pulse located at zero. It has infinite amplitude, and it's zero everywhere except at zero. Sorry, it's zero everywhere except at zero where it's infinite. And basically, it's a limiting. It's not really a strictly defined function. It's kind of a distribution, but basically the area under the curve is 1. So let's say the amplitude was 2. Then the bottom would be a half, etc. And as the amplitude gets bigger, the width gets narrower. So in the limit, then it's infinite at 0, and it's infinitely skinny as well. So that's the delta function. In reference 3 on the blog post, I have a blog describing how you can generate the impulse function. If you take the Fourier transform of an impulse function, you get a constant in the frequency domain. So a very, very narrow pulse has an infinite spectrum. And the converse, if you take the Fourier transform of constant in the time domain, you get an impulse at 0, which is the DC component. If you look at the exponential function, exponential j omega ct, that's equal to cosine omega ct plus j sine omega ct. It's like there's the I component and there's the q component. You can also express cosine omega ct as the sum of two exponentials. Cosine is an even function, and sine is an odd function. So if you take the Fourier transform of exponential j omega ct, you get an impulse at f equal to fc. So therefore, the Fourier transform of cosine gives you two impulses, one at fc and one at minus fc. If you mix two tones together, two cosines multiplied by one another give you the sum and the difference frequencies. And then here's the formula for a Gaussian pulse, which we'll look at. And what we can do here for the standard deviation is we can also generate an impulse using the Gaussian pulse by taking lambda, or the standard deviation, or I guess it's omega here, and turning it to 0. So let's look at GNU Radio. So here's a schematic showing how you can generate a cosine wave. This is a real cosine wave. So what we see there's your cosine signal. And in the time domain, since it's a real signal, you get two components. You get one at 1 kilohertz, and you get the minus 1 kilohertz as well, okay? And the level here, the relative level, is about minus 15. If I was to double the amplitude here, 20 log of 2 is about 6 dB, so that'll give you a relative amplitude of minus 9 now, about minus 9, so it's gone up by 6 dB. Let's look at the complex version. Now the complex version is basically cosine omega t plus j sine omega t, so it's like exponential j omega t, and that'll just give you one component. So there we go. Actually, I've got it set at an amplitude of 2, but there's your cosine there, the blue signal, and there's your sine. And you see we only have one component here at 1 kilohertz. It's at a level of minus 3. If I put this amplitude back to 1, we should see an amplitude of minus 9. It's about minus 9. So it's 6 dB more than the 2 tones for the real signal. Let's look at what happens when you multiply 2 tones together, 2 real tones together in the real domain. So basically you'll get cosine omega 1 times cosine omega 2. So basically you'll get the sum on the difference. So there we go, there's the sum at 11. There's the difference at minus 9. And you also get the image of that at minus 9 and minus 11. And let's look at the complex version of that. Now the complex version of that is 2 exponentials multiplied together. So basically you'll only have 1 tone at the sum frequency. So there we go. There we have the 1 tone at the sum frequency. So that's basically a quick overview of real and complex signals, as you can see in GNU Radio. Let's look at the Gaussian pulse here. There's a script file in Psychos Lab to generate the Gaussian pulse distribution. And SD, where's SD here? SD is your standard deviation. Let's start off at 0.1 and we'll see what happens here. So there's your Gaussian pulse. So it's almost down at 0 at 0.4, minus 0.4. Height is about 4. And let's look at the spectrum here around minus 50. So at around minus 50, you're out at around 5. Now let's decrease this to 0.05, which is half of that. And we'll see the pulse gets narrower and higher, and the spectrum gets flatter further out. So basically what we're in the limit now. We're looking at creating a Dirac Delta function. So now you can see it's quite narrow now. So it's down to 0 at almost 0.2. And you can see the spectrum here is much further out at minus 50 than it was before. So as this thing gets narrower and higher, the spectrum becomes flat. And so that shows you that with a Dirac Delta function in the time domain, you get a flat infinite spectrum in the frequency domain.